Welcome to my class. Today I want to give information regarding basics of automata. So this class is very useful for the second year, second semester students. So who are having formal languages and automata theory or theory of computation as a subject in their curriculum. Okay. So here I want to give the basic definitions regarding our automata theory. Okay, so let us see what are the basic terminology we have in the automata. So the first and foremost one is the symbols. So here the symbols are generally letters, digits, operators. So all those are comes under the symbols. So here we have the examples 0 to 9. These are specifying the digits, and small a to z and capital A to z, and the operators star, plus, minus, division, up to so on. All those symbols are operators are considered the symbols. Okay. And coming to the next term, that is the alphabet. It's a very important term in our automata theory. So here, an alphabet is a finite, non-empty set of symbols. And here, every time our alphabet is denoted with the sigma, the symbol sigma. Okay. So if you are defining the automata, our automata need to be defined over some alphabets. So here alphabet denoted with the sigma symbol, and our alphabet is a finite and non-empty set of symbols. Remember that. And what are the common alphabets we have in our automatas are? So binary alphabet, it's nothing but sigma is equal to 0, comma 1. And another alphabet is the English letters. So you may have sigma is equal to A, B, C, or sigma equal to A, B, C, D up to Z. Okay. So here the lowercase letters could be considered as the alphabets here. Remember that thing. And coming to the powers of an alphabet, what are the different characteristics we have for the alphabets? So if the sigma is an alphabet, we can express the set of all strings of an entire of a certain length from that alphabet by using exponential notation. Okay. So by using exponential notation means sigma power 0, sigma power 1, sigma power 2, up to so on. They are representing the exponential notations for our alphabet. So the sigma power 0 is indicating set of strings which are having the length 0. And sigma power 1 is indicating the set of strings which are having length 1. And the sigma power 2 is indicating the set of strings which are defined over alphabet sigma, and those strings are having length 2. Okay, like that. Okay. So here we have a general term, that is the sigma power k. So that to be a set of strings length k, and each of whose symbols is in sigma. It means that from the sigma, whatever the alphabets we have, with that alphabets we simply form the strings. Those strings length must be k. Those set of strings are appeared in our sigma power k. And sigma power 0, just now only we said that sigma power 0 is the set of strings which are having length 0. Length 0 in the sense they are having nothing. So it's nothing but epsilon. So here epsilon is one of the symbol which is indicating empty string, Okay. And see here, if sigma is equal to 0, comma 1, then sigma power 1 is indicating 0, 1 only, because here sigma power 1 is indicating the set of strings which are having length 1. So with these alphabets, we have 0 as one string and 1 as one string with this length 1. And sigma power 2 is indicating the strings which are formed with these alphabets with length 2. So with length 2, there is a chance of having 0, 0, 0, 1, 1, 0, 1, 1. In the similar manner, sigma power 3 is indicating 0, 0, 0, 0, 1, 0, 1, 0, up to 111. Okay. So like this, we simply define sigma power 4, sigma power 5, up to so on. Okay. And coming to the term string, string is a finite sequence of symbols chosen from some alphabet. So if you are considering our alphabet as 0, 1, sigma is equal to 0, 1, then our string is formed with 0 and 1s. If our alphabet is sigma is equal to a, b, then we simply form our string with AB. Okay. So here we have example W is equal to ABC is a string from alphabet sigma is equal to A comma B comma C. Okay. So like this we simply form a string by the alphabets, by the some alphabets. Okay. And coming to the length of the string. So the length of the string is nothing but the number of symbols in the string is called the length of the string. And that length of the string is denoted with the mod. Okay, so here if W is a string, then mod W is indicating the length of the string. Okay, so for example, W is the ABC, then mod W is equal to 3 because here we have 3 symbols in our string. So the length of the string W is 3. And coming to the null string. So here a string of length 0, string of length 0 is called the null string, and it is denoted with the epsilon. Epsilon. Okay, so here this is the symbol for the epsilon. And what is the mod epsilon? Mod epsilon is always 0 because epsilon is indicating the empty string. Mod epsilon is the length of that empty string. Length of the empty string is 0 only. Okay, so this is null string. And coming to the next terminology, that is the reverse of a string. So the reverse of a string is obtained by writing the symbols of the string in reverse order. So for example, if W is the ABC, then reverse of the W is denoted with W power R, and which is equal to the reverse of the string. So reverse in the sense CBA. Okay. And next one is the palindrome. So if the string and its reversal, if the string and reversal are equal, then we are saying that string is a palindrome. So if W is a string, then if W is equal to W power R, then we are saying W is the palindrome. And coming to the another term, that is the concatenation. So the concatenation is nothing but writing one string followed by other string. One string followed by other string. Writing one string followed by other string. Example, so here W1 equal to ABC and W2 equal to XYZ, then the concatenation of W1 and W2 is denoted with W1 dot W2. Remember that. The dot operator is indicating concatenation operator in automata theory. Okay, so the W1 dot W2 is equal to ABC. So this is a string W1 and followed by XYZ. XYZ is the W2. Okay. So remember that here the dot is called the concatenating symbol, the concatenating operator. Okay. And coming to the term prefix, here the prefix is the all leading symbols of the given string. All leading symbols of the given string. Suppose if the given string is W equal to ABC, then prefixes for this particular string are epsilon because leading of this ABC is the epsilon and A and AB and ABC. Okay, all these are considered as the prefixes for this string. Okay, and in the similar manner, we have another term that is the suffix. Here, the suffix is the all the trailing symbols of the given string. Okay, so trailing symbols in the sense if you are considering W as the ABC, after ABC, it means that from the right hand side onwards. Okay, so the suffixes are after ABC we have epsilon, so epsilon, and at rightmost we have C, and at from the second onwards, the rightmost we have BC, and from first onwards we have rightmost ABC. Okay, so we are considering these as the suffixes for our given string. Okay, and coming to the equivalence of strings. So most of the cases in our automata theories, we need to find the equivalence of strings too. So here, the definition for the equivalence of strings is, so if you are considering two strings. So when we are saying those two strings of the equivalence means, if they have the same sequence of symbols, they have the same sequence of symbols. So for example, if W1 equal to ABC and W2 equal to ACB and W3 equal to CBA and W4 equal to ABC. In this case, W1 is equivalent to W4 because here we have ABC and here we have ABC. The symbols are appeared in the same sequence. But here the W1 is not equal to W2 and W1 is not equal to W3. Even in these two strings, we have the symbols are same, but the order they appeared is different. Order the appear is different. So W1 is not equal to W2, W1 is not equal to W3, but W1 is equivalent to W4. Okay, so here the strings W1 and W4 are saying equivalent strings. Okay, and based on the definitions of prefix and suffixes, so we need to consider two more new terms. Those are the proper prefix and proper suffix. So the proper prefix uh, is the prefix of the strings which is not equal to the string itself. String itself is called the proper prefix. It means that if you are considering the string as ABC, then for this ABC, what are the prefixes we have? So the prefixes for ABC are epsilon, A, AB, 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 ABC. If you are not considering the ABC, and if you are considering the remaining prefixes, epsilon, A, and AB, then we are saying those are the proper prefixes. Okay, so the proper prefixes are not considering the string itself. Okay, and in the similar manner, we have another term that is the proper suffix. So here the suffix of a string which is not equal to the string itself is called the proper suffix. The same, if we have the string as ABC, then the suffixes are general suffixes are epsilon, C, BC, ABC. But the proper suffixes are epsilon, C, BC only, because ABC is string itself. So it's not a proper suffix. Okay. So these are the proper suffix and proper prefix. Okay. And coming to the next one, that is language. So in our automata theory, in every time we are using this term language. Okay. So the language is a set of strings defined over a specific alphabet. Specific alphabet. Okay. So if we have a specific alphabet sigma as some AB, then a set of all strings which are defined over the AB are called the language for that particular alphabet. Okay, and if that particular set is finite, then we are saying that is the finite language. Otherwise, it is called the infinite language. Okay, it means that if the defined set is not finite, then we are saying that is the infinite language. So here we have an examples. So let us say sigma is equal to a comma b. It is an alphabet, and L1 is equal to x such that mod x is equal to 2. So mod x is equal to 2 means, so the strings, the set of strings which are defined over a comma b, and the length of the strings is equal to 2. So here the length of the string is equal to 2 means we get the strings are a b, b a b. Okay, so these are the set of the string. And here we are saying this is the language, and this particular language is the finite language, because here we have only 4 strings under this language. 4 strings in the sense it's a finite number. So we are saying this is the finite language. And consider the another example, L2, which is equal to set of x such that mod x is even. Mod x is even means the length of our string is even. The length of our string is even means, so it may have two, the length of the string is either 2, sorry, it may have the length as 2, 4, 6, 8, 10, up to so on. Up to so on. There is no bound, upper bound. Okay. So we simply get L2 as set of A, B, with length 2, and sorry, 4As, 4Bs, and A, B, and B, A. So like that we have the length 4 strings too, and come up to so on. Okay. So this so on is indicating that you may have any number. It's not a finite. That number is not a finite. It's an infinite number of strings appear in this particular language. So we are saying this language is an infinite language. Okay. This is the basic difference between our finite language and the infinite language. In the finite language, we have finite set of strings, and in the infinite language, we have infinite number of strings. Infinite number of strings. Okay. And coming to the very important terms in our automata theory, those are the Kleene's closure and positive closure. So here we are defining our Kleene's closure over an alphabet set. So here Kleene closure need to be denoted with sigma power star. This star is indicating Kleene closure. It's nothing but a set of all possible strings which are defined over an alphabet sigma. It is defined on alphabet sigma, and this one be denoted with sigma star. Okay, so the sigma star is equal to sigma power 0 union sigma power 2 union sigma power 3 up to so on. What is the meaning of this? Sigma power 0 is indicating that the set of the strings which are having length 0. And what is sigma power 1? Sigma power 1 is set of strings which are having length 1. Sigma power 2 is set of strings which are having length 2. Set of sigma power 3 is set of strings which are having length 3. Like that, we have all of the strings, all of the possible strings over the alphabet sigma is called our Kleene closure. So what is sigma power 0? Sigma power 0 is nothing but empty string set. Empty string set means, so the strings which are having length 0. How we are denoting those are denoted with the epsilon. So it's nothing but sigma power 0 is nothing but epsilon. Okay, it means that here our Kleene closure is allowing epsilon, and it allows the all possible strings over the alphabet sigma. And coming to the another term, positive closure. So the positive closure is denoted as sigma power plus. Power plus is indicating positive closure. Star is indicating Kleene's closure. Okay. So here the positive closure is the set of all possible strings which are defined over an alphabet except epsilon. What is that epsilon? Epsilon is the sigma power 0. Sigma power 0. So here except sigma power 0 or except the epsilon, whatever the strings we have, which are defined over an alphabet sigma. So that one we treated as our positive closure. With the positive closure, sigma power plus is equal to Kleene closure minus epsilon. Minus epsilon. Okay. So this is Kleene closure and this is the positive closure. Both terms are very, very important in our automata theory. Okay. And along with this, we have another term, that is finite state machine. Finite state machine. Okay. So here finite state machine is any system with finite number of states. With finite number of states. Okay. So here we have two examples. See here, on and off. This is indicating a finite state system for the switch. Okay. So if we are in the on position or on state, if we are pushing it, then we are going on to the off position. And if we are in the off position, by pushing, we are simply going into the on position. Okay. So here we are considering on as the start state. If you are considering off as the off state as the starting state, then we simply get the machine our finite state system be as like this. Okay. So these are the important terms which are required for our automata theory. Okay. So in the next video, I will start the finite state machine. What is finite state machine and what are the different types of finite automatas we have. Okay. So we will discuss, I will discuss that topic in the next video. Okay. Thank you.